get is actually log smooth over A1, and this will be the object we're trying to study now. And yeah, and the logarithmic Gromov-Witten theory provides a very nice theory to talk about the Gromov-Witten invariants on such log smooth space. Okay. And the cool thing of it is that logarithmic Gromov-Witten invariants are deformation invariant. So if we want to study the Gromov-Witten invariants on the central fiber, where on the generic fiber, where right now we don't have like any log structure on it, so it's the same as the ordinary Gromov-Witten invariants. And we can study the Gromov-Witten invariants on the central fiber, and in their algorithm that we can specify the irreducible components of the moduli space to the of the maps to the central fiber by using the rigid tropical curves. So a natural next question is that, so after we know what kind of types of the maps we are looking at, then we try to relate the log Gromov-Witten invariants on each components of the central fiber with the log Gromov-Witten invariants on the entire central fiber. Therefore, it will give us the Gromov-Witten invariants on the general fiber. So this is the question that I'm trying to give an answer to. And in general, I'm trying to give an answer in in the situation that the gluing strata is a toric variety. So here is a brief history of our exploration of this question. So so in 2001, in Simplexes by Li Ran and and also by Ilona Parker, that they built the relative Gromov-Witten invariance theory, and it is for the case that we have the central fiber has two components and they glue along a smooth divisor. And in the algebraic side, it's done by Jing Li. And yeah, sorry for the typo here. I think it's 2002. Yeah, and later on there were some refinement or different approaches to this question. So Kim in 2010 built the logarithmic stable, used the logarithmic stable maps added to the picture, and I think Abramovich and Fantecchi, they introduced the orbifold techniques for this problem. And yeah, so but when they try to glue together, at that time, expansion technique is probably the only way or the best way that we can try to solve this type of question at that time. And in 2019, Ragnanthan used the logarithmic expansion, and he generalized the case to the general normal crossing settings. And yeah, so today the technique or the method we're gonna use will be different from them, because we do not try to modify the target and try to take the expansions to try to solve the problem that we met during the deformation, but we use the punctured log Gromov-Witten invariant on it. So yeah, so the thing I'm going to present today is kind of like the first try along this way. So what are the punctured invariants? And so let's see an examples. So first we start with a stable map to the central fiber we're interested in, and we are considering the type where we have, for the curve, we have 4 components, and so the map maps one of the components, contract one of the components to the central to the center over here, and for other 3 maps, they are mapped to the 3 different components of the central fiber, and it's mapped generically, and we add 2 mark points for each of the, for two of the curves. Okay, and then we will try to split the curve that we start with. And that's where the punctured come from, because so if we split a node, then we will get so after we split these all three of the nodes, we get four components of the curves, and each node we split, it becomes two punctures for each of the components that it's connect to. And so after the splitting of this map of this curve, we get four components of the four separate curves, and two of them has one marked points, one punctured points, one of them has one punctured one, and the C4 over here, it has three punctured points. And we use a type tau to pack the discrete data of the map, including like where including the dual graph of the curve, and where we send each component of the curve to, which strata we send each component of the curve to, and also we marked where we send the mark point and also the nodal point and the curve class. So after splitting, like the discrete data also split into four separate discrete data. And we define a punctured map to be marked by a type tau by basically means that this map lies in the closure of the open locus of the maps with type tau. Okay. And the theorem by Abramovich, Chen, Gromov, and Siebert says that this moduli space of basic stable punctured log maps marked by tau is a proper Dillon-Mumford stack. And also for the splitting process we just go through, there is a natural finite representable splitting morphism between these moduli spaces. So the next question we are trying to think about is, how about the other direction, that after like what's the relation between the glued type, the moduli space of the glue type with the moduli space of the split type. And so in this example that we see, since we are we contract the whole like C4 from here after the splitting, that like schematically, like all the gluing will happen at the central point. And but this point is not a trivial point because it has a log structure on it. So the point, the gluing will all happen on a log point from here. But like, so this is the subtle thing, because gluing along like gluing along like objects with log structure is very hard, and even if it's a point, it's already like very subtle. Okay. So let's see an easier example, that we first try to glue along a point with the log structure n over here. So suppose we are trying to glue two points along this point. And if we are taking the map F, like on the schematic level, it's going to be the trivial map. But on the log structure, we can take it by multiplying it by 2. So we send 1 to 2 on the monoid. And if we try to take the fiber product in the category we want, which is the fine saturated logarithmic schemes, we will get the disjoint union of 2 points instead of like maybe 1 point that we like everyone would hope it for. And so for these 2 points, one of the points sends the log structure here t to t, and the other one sends it from t to t minus t. Okay. So why does this occur? And so the reason of it is the additional log structure. Actually, we can feel it as it remembers a normal bundle of that point, a line bundle of that point. So if we try to like go back and embed this point onto a line, and the multiplying it by 2 on the monoids will correspond to with sending this line by taking a square. So it will be T maps to T square. And if we take the schematic fiber product over here, we will get a union of 2 lines. And so the diagram on the left schematically will be the pullback of the central point of this union of 2 lines. But yeah, so it's actually a double point, like if we kind of like remember the neighborhood of it. And the logarithmic fiber product in the good category that we want normalize the double point. And that's the reason we get a disjoint union of 2 points on the left. Yeah, so this example already like shows us that the logarithmic gluing is very subtle, but like the celebrity news of this is that it's like not very close to the schematic gluing, but somehow it's very close to the tropical gluing. So it's closely related to gluing the tropical spaces. And yeah, and the lemma by Sam Mocho that I learned from in I think in one his note on archive is the fine saturated logarithmic fiber product of toric varieties is a disjoint union of M toric varieties. And each of this toric variety is isomorphic to the toric variety associated to the fiber product of the fence. So yeah, so it means that like we can use the tropical insights of this question to try to do the gluing in the category we want. And especially in the case that we're interested in, this multiplicity M is a lattice index because I will mention it later because the space we're interested in has the idealized log smooth morphism. Okay. And yeah, and the cool thing is that the virtual gluing of the punctured invariants admits a toric model. And as already mentioned in Dan's talk, that the virtual gluing happens on the space which is related to the artin of X, and this artin is like the static version. Oh yeah, can you see the? Okay, I'm. Okay, yeah. Yeah, so the artin of a log scheme is an algebraic object that connects the geometric picture with the tropical picture. And so, yeah, so the like a very like my favorite fact of artin probably like is the homomorphism from a curve, a log curve to X, bijective to the homomorphism on the tropical level, that the tropicalization of the curve to the tropicalization of the X. So yeah, so it's intrinsically like a tropical object, but it's like algebraic. And yeah, and as already mentioned in Dan's talk, that the moduli space of maps to this artin is idealized log smooth, and we have a perfect obstruction theory of the moduli space of maps over this moduli space. Yeah, but in order to like talk about gluing, that we need some modification of this space because right now like the artin is a static object and we do not have the schematic structure on it yet. So first we try to enhance it with the scheme structure. Yeah, and this is the diagram that Dan showed us on the last page, that there is Cartesian diagram of this where the horizontal maps are proper representable and the vertical maps provides the perfect abstraction series. And yeah, so the case we're trying to study will rely on we're trying to interpret this this morphism, like we were trying to study this morphism. Yeah, so there is another like more subtle thing that we need to take care of is that in order to glue logarithmically, a further enhancement of this space is needed, and we want to add like, yeah, so we need to modify like the log structure on our moduli space, and there is a Cartesian diagram of this where this is where actually like the gluing happens, and yeah, and so I will not go into very like details of what this actually means, but I will show you like a pretty nice fact is that the child theory on this space with the map we had on this space are actually kind of like almost identical, that there is an isomorphism of the underlying stacks between the reduced induced structure on this space with the space that we're actually interested in. Yeah, so first yeah, so this diagram will be the like the key objects that we're going to work on. And a first observation of this is that the evaluation map over there is idealized log smooth. And yeah, and as remarked before, idealized log smooth is approximately locally a closed immersion of the toric strata into a toric variety together with a toric morphism. And so if we look at this space, we will need to analyze that what is this toric closed immersion and what is this toric morphism. Yeah, so for the toric morphism part, it can be captured by the tropical evaluation maps. And yeah, so first, as mentioned by Dan, that we have a basic log structure on the moduli space, and it is the universal log structure that we put associated to this type. And dually, like if we think tropically, the basic cone is the universal family of the tropical maps to the tropicalization of X of this same type. And so, and remember we did a modification of our log structure. So we are no longer using the basic log structure, but the evaluation log structure that we are using over there has the same like spirit, that the dual cone of this is the universal family of the tropical maps with a marking on each of the evaluation edge and leg. And the tropical evaluation map that we are having over there is simply that we evaluate at the markings that we added. And as for the closed immersion part of the toric strata, it's related to an ideal structure, which comes from the marking, comes from the puncturing, and also comes from the evaluation marking, that the additional marking that we add. But in any case, that this is totally defined by the tropical type. So this ideal structure is actually a tropical object that we don't yeah, so we don't need to know much about like the real target other than the tropicalization of it. So let me give an example of the things I just mentioned over here as yeah. And so suppose for the central fiber that we're looking at, and remember we put the divisorial log structure on it. So the tropical space, this will be r log or equals to 0 cube, where the central point over here, the dual of it is going to be like the whole tropical space. And yeah, and if we take a slice of this by saying, yeah, so if we take like the slice by x1 plus x2 plus x3 equals 1, just to trying to like visual it more to it, associated to this type of the map will be regenerated. Okay, yeah, it seems my internet was a little bit unstable. Is it fine? Okay. Yeah.
You were a little bit rough for a few seconds, but it's fine.
Okay. Oh yeah. So I'll like quickly mention that the thing I said. So yeah. So for the tropical space of this x of 0, it will be r larger or equals to 0 cube, and the basic cone of this type will be generated by the image of the central vertex over here. So if we take a slice of x1 plus x2 plus x3 equals 1, that it will actually be rigid over here. So this is the tropical map of the type over here. And because we needed to satisfy the balancing condition, that the only choice that we can have is this one. And the basic cone will be the cone generated by this one. And as for the evaluation cone, it's simply we add an additional marking for each of the edge and each of the marked points, or each of the puncture. And since over here that these two marked points that we the contact order of them are 0, so so the tropical map, they are always mapped to the vertex of C1 and C2. So it does not contribute to the evaluation cone. But for the 3 edges that we are adding here, that we add 3 free variables that we can move along the direction of the edges. So the evaluation cone of it will have 3 more additional vectors, and we want it, since like these are the punctures, and we have to add the requirements that this edge does not extend to outside the tropicalization of x of 0. So this edge will move inside the range of the tropicalization. And the tropical evaluation map is simply we map the edge to the additional marking that we are adding here. So the last ingredients that we will need to use, and it is kind of like in the spirit of the final splitting formula that I'm going to present, is a classical fact of Fulton and Stemfeld about the intersection theory of the toric variety. And yeah, and as I mentioned before, that the fiber product that we're doing is very closely related to the toric varieties. And the tropical picture with the algebraic picture actually match like beautifully in the category of toric variety. So yeah, so let's take a look of this one. So suppose we're having an x being a toric variety, and sigma x and x is the fan structure of it, and we're trying to study like the diagonal map of the toric variety. And so a vector v in the target lattice defines a GM action on x times x, which comes from the one parameter group associated to it. Oops, another typo, sorry. Tx times Tx. Sorry, I think Okay. So geometrically, if we take the limit t goes to 0 by this GM action, we'll get, like, after we push it along the limit, we'll get a torus invariant subscheme that is rationally equivalent to the image of the diagonal map. And complementarily, if we displace the image lattice by this vector v, we can read off like the cones that contribute to this torus invariant subscheme directly. And the Fulton-Sternfels formula tells us in the Chow group of this, in the Chow group of x times x, that this push forward map can be read off by, we simply displace the image strata by this vector v, if we pick the vector v to be general enough. And let's see an example of this. So if we are considering the diagonal map of P1 maps to P1 cross P1, and this will be the fan map of it. And if we pick a general like vector v from corresponds to the 0, 1 point in the lattice, that, and if we move the image lattice along this direction, and we can find the intersection point, which is this lattice with these two subcones of the fan of P1 cross P1. And geometrically, we will have, this is the image of the diagonal map, and we're simply adding a GM action on it. And when we take the limit, t goes to 0, this strata is mapped to the union of two toric invariant stratas, which are the cones correspond to the, which are the toric stratas correspond to the cones that we read off by the combinatorial picture. And so if we think of the toric varieties with the toric, the canonical toric log structure, a displacement factor actually defines a log structure compatible deformation of the image delta of x inside x cross x. And this is the key ingredients that we are using over here. And this is the part that we can generalize to the case which are not toric varieties, but also but only like locally toric morphism. Yeah, so this is the splitting formula of the punctured invariants that is probably like the main result I'm going to present today. And the assumption is the gluing strata is isomorphic to a toric strata of a toric variety. And it's basically like the same as we are assuming that we're gluing along a toric variety with the toric log structure. And the two ingredients that we're also needing here is, one, we also want to have a generic displacement factor. And two is that after displacing it along this vector, we'll get the types that will be on the limit when we push along that direction. Yeah, and the theorem is that there is a virtual push forward map from the of this delta from the moduli space of the glued types to the moduli space of the split types. And a direct corollary of this will be a numerical splitting formula. Suppose we have, since we know we have a natural evaluation map from the moduli space. So from the moduli space of type tau to the target space. And suppose we have a cycle decomposition, Kunis decomposition of the cycles, then the Gromov-Witten invariants that can be obtained from the splitting formula, that we can actually compute the Gromov-Witten invariants on each separate types, and we will obtain the invariants that we want. Okay. So let me give an example of this. Like, let's go back to our favorite example. So in this case, we know that this is the type that we are looking at. This is the rigid tropical curve, and we are trying to displace it a little bit. And by a dimension count, we actually realize that the expected dimension on the separate types will be just one dimension higher than the dimension that we already start with. And the reason is over here that this is a rigid tropical map, and the tau associated to it has dimension equals 1. Okay. So in this case, displacement along one edge already gave us the types that we want of the expected dimension. And from here, we can see that if we displace it, like maybe along this direction a little bit, we will obtain 3 separate types. And in the first case, it will correspond to C1, C2 map generally, and the C3 degenerate into one of the strata. Yeah, so I have another picture over here trying to explain this. So in this case, that since we degenerate C3 into a deeper, a larger cone, and it will correspond to that the C3 starting from here, and it degenerates into this strata. And similarly, for this case, we degenerate C2, so it will be C2 degenerate from where we start goes to here, and similar for the third type. And if we further add the assumption that if we further require the marked points to pass through 2 general points, then the marked point lies on C1 and C2, and only the first type will contribute to the Gromov-Witten count. And yeah, and that's actually how, like, if you're familiar with the decomposition paper, the degeneration example that mentioned in the paper of Abramovich, Chen, and Siebert, that this will give us the Gromov-Witten count 1 in this case, as they mentioned in the paper. Yeah, so I will present a first application of this is a reproof of the Nishinou Siebert correspondence theorem. And so let me recall, like, the theorem. What's the question that we're trying to study is if X is a Toric variety, and we have some subspace subschemes which are the closure of the subtorus of the maximal torus in X, which are the subvarieties defined by the linear subspace of N of X, and how many N marked point rational curves are there in a Toric variety with ith marked points lies on the strata that we specify. And a translation of this question to the log Gromov-Witten setting will be if we consider a type tau with a graph containing only one genus 0 vertex, and with n contact order 0 legs, and what is the degree of the, I should mention that the image of this will be, we have n legs, and we map to our X, and I'll maybe like draw P2 as an example. And the type we're looking at is we simply map it to the middle vertex. So what is the degree of the virtual fundamental class of this moduli space, where we obtain it by taking the fiber product over the inclusion of the marked points. Yeah, so the strategy to so the strategy that we're using here is, it's embedded in the idea that, like we mentioned before, that virtually this will be an idealized logarithmic map, and over here this is exactly a Toric morphism. So if we are picking a generic displacement vector on the Toric space of this x to the n, it will pick, like by a dimension count, we will obtain a finite collection of the tropical types, and these are the tropical curves that the Nishinou and Siebert paper mentioned. And so after we choosing a generic displacement vector, and we pick out the tropical types, and actually, since these are the general ones, we can perturb it a little bit to make it lies on the maximal cones. So yeah, and if we split along all of the edges for each type of them, that we will get actually a degree zero map. From a virtually degree zero moduli space to a product of moduli spaces, which also has a virtual dimension zero. So the only, so if we're trying to count like the how many algebra curves that we're going to get, the only thing we need to do is we try to count the multiplicity, and and the splitting formula provides the multiplicity. And another application is, I think, I don't know why that my screen, okay. Yeah, so another application is the intrinsic mirror symmetry, and which I don't know much about, and like Bernd will talk about it like in the next talk. So the natural next question is to ask is that what if the gluing strata is not toric? So this is a part that like from the displacement vector V that we can get some insights from, because that displacement vector actually defines a rational deformation of the image f of x inside x cross x. Sorry. Inside x cross x. And so in other words, that a displacement vector provides us with a family of maps over A1, where on a general fiber, this map is isomorphic to F, and on a central fiber, that this will degenerate, and the Phantom-Stern formula will provide us with how it's degenerated into. So if we're trying to like generalize it to the general case, that we will have to consider like under what cases such generic degeneration should exist for the gluing strata. So if this already exists, for example, like for the Toric stratas, for the Toric varieties, and or for if the gluing strata has constant log structure, then this generic degeneration, we can always find it. But and then we can take the fiber product. Also, this will be our moduli space, and we can take the FS fiber product over here, and the tropical information should help us to single out the stratas that where like this space on the central fiber will contain. So maybe the next question that we will try to answer is that what are the conditions for such generic degeneration to exist in general? And and right now I don't have a very good understanding of this question. And obviously I go like too fast, and that's the end of my talk. And thank you for your attention.